Hello everyone, welcome back to second part of our scalable data mining lectures on Hadoop. So as we discussed, a Hadoop MapReduce system has three main phases. So the first phase is the map phase. So in the map phase, user writes the mapper code. Okay. The input to the mapper is an unstructured record. It can be of the form key value pair, or it can just be a line which is stored in value. Okay, so examples are maybe a row of a RDBMS table, or a line of a text file, or an image, things like this. The output record is of the form key value pair. Both key and the value can be anything, like they can be text, they can be numbers, etc. And generally there is a way to separate the key and the value. So for example, the output could be something like column ID comma value. For each row you may want to extract the column ID and the value in that column as the mapper output record. Okay, or you could have something like word or count. Now the second phase, which the user does not have to code, is the shuffle or the sort phase. So how does the so the shuffle phase ensures that mapper output records with the same key value goes to the same reducer. Okay, so remember that in a distributed setting, the mapper task could be performed in one computer, and the reducer task could be performed in another computer. Okay, so in any case, the mapper output records have to be transported to the correct reducer. Okay, and the shuffle phase, which is run on the mapper side of the code, ensures that the mapper output record with the same key value goes to the same reducer. We will see how. Okay, and the sort phase, which is usually run on the reducer side, okay, though part of it may also be run on the mapper side, ensures that among the records received at each reducers, so a reducer may be receiving many records from many different mappers. Okay, so the sort phase ensures that the records received at each reducer, of the records, the ones with the same key value arrives together for processing. So in other words, you can form a structure like key comma a list of values, so v1, v2, and so on and so forth. Okay, so this format could be achieved. Finally, the reduce phase, again the reducer is a user defined function which processes the mapper output records. So uh, with some of the keys output by the mappers. This is important to note, that each reducer will get a subset, will typically get a subset of the keys output by the mapper. It may or may not receive all the keys output by the mapper unless there is only one key or there is only one reducer. Okay, so again the input is of the form key value pair. Now here one could also have key list of values, but as we discussed, they are effectively the same, and the implementation changes. It changes from implementation to implementation, and all records having the same key arrive together. So and then output is a set of records again of the form key value. Okay, but many times key is not important unless the output is again chained. Sometimes the key may be important. Actually, many times the key is important. So yeah, so this is basically the parallel picture. So you can think of, there is the input phase, then there is the mapper phase where there are many mappers running. So mapper 1, mapper 2, mapper 3, and then each mapper outputs many records, and depending on their keys, the records may either go to reducer 1 or they may go to reducer 2. And this is true for all the mappers, okay? Because the requirement is that records with the same key should go to the same reducer, okay? And finally, each reducer processes the data and produces the output. Now, this is a run through of the word count example that we discussed in the multi-server or multi-computer scenario. Okay, so in the map phase, let's say the server 1 has this file. John has a car which has no radio, so it outputs John has. There are two has here, so it is directly saying has 2, but actually what is happening here is it will be output as has colon 1 and then another has colon 1, and then there is a way of combining things. So there is a method called combiner which can do this, okay? But essentially this is server 1 output. This is so this is the mapper output of server 1, this is mapper output of server 2, and this is mapper output of server 3. Now the MapReduce system has decided that the key John has A and red will go to the reducer in server 1. Okay, so there are 3 reducers now. So, so these keys will go to the reducer in server 1. Car, which, no, radio and Mary will go to the server 2, and bicycle, Bill and or will go to server 3. And you can see that there is a has record from server 1, there is another has record from server 2, and there is another has record from server 3, which all come to server 1 for the reduce task. Similarly, there are 2 car records, one from server 1, okay, and another from server 3. Both come to reducer 2 for output. And finally, after the reducer has run, all these counts 2, 1, 1 will be added to produce has 4, 2, red 2, car 2, which 1, no 2. So there are 2 nodes, one from server 1 and another from server 3, and so on and so forth. So this will be the reducer output. So note that reducer output is also generated in multiple parts, and there need not be any ordering among these parts. Here is another example. Suppose you want, suppose you are given, timestamp, so date and time, and you are given the temperature of temperature reading at that particular timestamp. So let's say there are weather stations, and these weather stations at a particular time, let's say at a particular hour and at a particular date and a particular year, is recording the temperature at a particular place, okay? And you want to find what is the max and the minimum temperature for the last century, okay? So you need to first take as input, so let's say in this case your input is of the form, or the mapper input is of the form temperature followed by a date. So this is just a record ID, and you in the values you have the temperature followed by the date, okay? And now your mapper will output the record year, okay, and the record temperature, recorded temperature. But it will only output the recorded year and the recorded temperature if the recording is from the last century. So let's say you have data from something like 1930s to 2020. It will not record any data which is after 2000. Okay, so it will only output those records which were there in the uh, from 1930 to the year 2000. Okay, yeah, so it will just output this. Okay, now in the shuffle page, so remember that the mapper output key is just the year, and the shuffle phase will then send all the records for a particular year to a particular reducer. Okay, so your mapper output key, okay, is year comma temperature only if the year is between 1930 and 2000, and your reducer input key will also be of the same format. All the data for the same year will be processed by the same reducer. Okay, so the reducer will take a maximum of a given year and output that record. Okay, so the reducer output is maximum or minimum depending on the case. It will output either the maximum or the minimum for the given year. So at the end of it, again, you will have for the years 1930 to 2000 all the maximum and the minimum temperatures. And now, so one can just take the maximum of these, which is just a maximum of 70 numbers, which can be done in very fast on a single computer. Okay, so in a nutshell, what does Hadoop MapReduce provide? Hadoop MapReduce provides automatic parallelization and distribution. It provides fault tolerance. So all the reducer, mapper and reducer's jobs which are running on multiple computers uh, will be restarted, or we will see how it provides the fault tolerance, but essentially it will take care of the fact that all these jobs finish, and they finish in the right order. Methods for interfacing with HDFS for co-location and computation, co-location of computation and storage of output. Okay, so it provides all these methods so that the user does not have to bother about these things. So the user only has to write the mapper and the reducer code. It provides status and monitoring tools for the jobs. It provides an API in Java, and also it provides the ability to define the mapper and reducer in many languages through Hadoop streaming. Okay. Now we will go into the details of Hadoop distributed file system, which is the distributed file system of Hadoop. So HDFS, or Hadoop distributed file system, is a distributed file system that is fault tolerant. So first, one has to understand that the file system itself has to be fault tolerant. Okay, and it is scalable. So it is very easy to expand, in the sense that if you have an existing file system, you can just add new servers, and you have to provide the directories on those servers, or the locations on those servers where HDFS should store data, and HDFS will automatically expand to use the space in those servers. Okay, it is the primary distributed storage for Hadoop applications. HDFS provides interfaces for applications to move themselves closer to the data. Basically, it provides the locations of the data that the application is going to work on to the application, so that the application can then run where the data is. This is called data locality. So we will think about it. We will discuss about it. So this is called data locality. HDFS is designed to just work. Okay, so basically it's like all the faults or all the underlying things are sort of hidden from the end MapReduce user. Okay, now what does HDFS consist of? So HDFS consists of two main components. These are basically programs or background tasks or daemons which run on the machines on which the HDFS is running. So the first one is the name node. Okay, so the name node is the heart of HDFS file system. It maintains and manages the file system metadata. So basically it manages the list of files that exist on this entire file system and the locations of the blocks that make up a file. Okay, so on which of the data nodes are these blocks stored? So this is what is stored in the name node. And the data node, so name node runs only on one of the machines, and that is known to the Hadoop system where the name node exists, okay, or on which machine the name node is executing. Data node, on the other hand, runs on every machine, okay, and the data node communicates with the name node and it also communicates with the applications, okay. So the data nodes actually stores the data, and as I mentioned, the data node process runs on each of the machines. Okay, so this picture gives an idea of how the HDFS operates. Okay, so the HDFS has this central name node. Name node has this metadata, so it will typically have the name of the file, okay, the number of replicas, and then it will have a list of blocks where these files are stored and the location of those blocks. Okay, uh, so when a client tries to read some data, it uh, provides the path of the file to the name node, okay, and the name node provides the list of blocks, and then the client can go ahead and directly read from the data node. Okay, similarly the client can also write directly to the data nodes, and we will see how the read and write happen. Another thing is that the name node and the data node periodically communicate with each other to provide things like replication, or if a particular, so the name node should know if a particular data node is down because the server has gone down, or some such eventuality. So in order to ensure fault tolerance and redundancy, the data nodes and name nodes periodically talk to each other. So the data nodes talk to the name nodes, and then they also talk to each other. So what are the design assumptions of HDFS? So the first is that hardware failure is a norm. Okay? Second is, as we mentioned, uh, so access to most of HDFS data is a streaming data access. So HDFS performs best when the data access is of a streaming form. Okay? And that is not a random seek access, but an access one after the other. Okay. And secondly, it's very important that your applications or applications that use HDFS should follow the format write once, read many times. Okay, so important data should be written to HDFS once, and then since the data is important, hopefully it will be read many times and processed. Okay. This is another input thing. It is designed to be high throughput but not low latency. Okay. So the first request for a block of a file to HDFS may take a lot of time to process, but when an application makes requests for a bulk of lot of blocks, the total throughput is very high. Okay, and it is designed to handle very large files. Okay, so these are the characteristics. It performs best with a modest number of large files. It is optimized for streaming reads, so it does provide a list of data data blocks of a file to the client, and the client side, so the client uses the Hadoop libraries to read from HDFS, and these read methods are optimized in such a manner that they actually take a list of blocks and they read the blocks one after the other, even though in a streaming manner, uh, sort of like parallelly. So that is how they interact with the data node. And this is a layer on top of the native file system. So one still needs a native operating system and a file system, and the blocks of Hadoop are really, you can think of them as files on the native file system rather than on the raw hardware. Data is organized into files and directories, just like the Unix file system. Okay, files are divided into blocks and distributed to nodes. Okay, uh, the block placement is known at the time of read, and so the computation is moved to either the same node where it can be read, or maybe to a rack local nodes, because transfer of data, even if the node on which the data is present is not free, the data can be transferred to another node on the same rack, which is just over one switch, much faster than uh, if it has to be moved to any other server on another rack. Okay, and finally there is a replication that is used. So each block is replicated, and replication helps in all these three. So it helps in speed, in the sense that you have the choice of where to schedule your jobs, because you have the data available on, suppose the replication factor is 3, then you have the data available on 3 different machines, and the machine which is most free, the job can be the mapper job can be scheduled on that machine. Okay, uh, and then it is used for, of course, fault tolerance, because if a particular machine with the block dies, there are still two other replicas of that block, and the job can be moved to one of those replica machines. And finally, for self-healing, so like I mentioned, the data nodes and the name nodes talk to each other periodically, and whenever a particular data node is down, name node makes sure that other data nodes actually replicate those blocks onto other machines, so as to keep the replication factor constant. Okay, so we have seen this architecture. There is also something called secondary name node, which is kind of a backup for name node. In case the name node fails, the Hadoop system starts contacting secondary name nodes, and the secondary name node also has the same metadata as the name node, and then it can store all the so the HDFS can continue operating, and in fact, one can also once the name node server is restored, one can also restore the data back to the name node. And these are the key tasks apart from interacting with client. So replication is a key task. Balancing is another key task. Balancing basically makes sure that the data is balanced across the data nodes, and heartbeats is to ensure that the name node knows which of the data nodes are up and running and which are down. Okay, so name node metadata. So the name node stores the entire metadata for the entire file system. Now the entire metadata is stored in the memory by the name node. So what must ensure that the server that runs the name node has a very high memory, and this is very important for the performance of the system because the name node accesses the metadata a lot. Okay, so what does the metadata has? It has the list of files, it has the blocks for each file, it has the data nodes for each block, okay, and it has the file attributes like creation time, replication factor, etc. Okay, and the name node also stores the transaction log of the file system like records of file creation, file deletions, etc. Okay, a data node has basically these components. So it has the block server. So the block server basically stores a particular the data in a particular block. Okay, so a block is typically, you can think of a block as 128 MB of data. So typically in most configurations you will store 128 MB of data, but this is of course a configurable parameter and you can change it depending on the total size of your data, the kind of files that you will have, etc. Yeah, and so each block is a file in a local file system, e.g., ext3 file system for Linux or something like that. Okay, it stores the metadata for each block is the CRC. So for checking corruption and all these things, and it serves this data and metadata to the client. So when a client reads a block, it serves this data to the client. Okay? And also when a client writes a block, the data node takes the data from the clients, and either client or another data node. It can take data from both as the case may be, and it can create a new file for a block and write it. It periodically sends a report, a list of all blocks to the name node. Okay, and we will come to the pipelining. This is basically how replication is achieved. Pipelining is the method by which replication is achieved in HDFS. Yeah. So and we will discuss how this is achieved. Okay, so how does the user interacts with the HDFS? So the user interacts with the HDFS by using mostly all Unix-like commands. So if the Hadoop system is installed, it will either have a command like HDFS or it will have a command like Hadoop. Typically both works, and then you have to say HDFS DFS or Hadoop DFS, and then you have to give the command as an option. So for example, -ls is for list, and it takes many options which are very similar to the Unix options. So I will not go through all of them here. I have listed some, but you can check when you have a system installed. Uh, it can have commands like list. It can have commands like disk usage. So it will display the disk space used by files, let's say in a particular directory. It will have It has commands for creating directory, commands for copying data from the local file system to the HDFS directory, and this is for recursive writes, recursive listings of directories, and then you can also have uh, commands for copying data from HDFS back to the file system. So if your local data is tutorial slash data, then you can use command like HDFS DFS copy to local, and then this is the path on the HDFS, and then this is the path on the local file system. And then you can also check whether the data has been copied faithfully or not. You can also get the access control lists. So you can get all the access control lists. You can get statistics like the size of a particular file or replication factor, etc. And you can also uh, write data to HDFS by directly piping it from a program. Okay, so this is also sometimes useful if your data is too large to be stored on the local file system but being generated from another program. Let's say it's coming from a stream or you are downloading it from the internet. You can directly put it onto a HDFS distributed file system using this command, this HDFS minus put command. Okay, so how does the HDFS read client operate? Okay, so remember, a client here is a program which is trying to read data from the Hadoop distributed file system. Okay, so step one is it has the file URL. It calls open on the file and talks to the name node through this distributed file system class. Okay, and then it requests the name node to get the block locations. Okay, once it gets the block location, it creates this object called fs data input stream. Okay, so this is basically the object which controls the read of data from this particular file throughout the read procedure. And as I mentioned, this read operation is optimized for streaming reads. So the system performs much better if you read the entire file from beginning to end in order. And how does that happen? So what this fs data system does is it it already has the list of block locations, so it fires up this read command, okay, on each of these data nodes, and typically it does not wait for the output to arrive or this read to complete. So output actually never arrives to the client machine. So typically the operation will be performed on the same node as the data is there, or on another node. Okay, and so this will be in the form of typically a mapper task. So the mapper task will be created on this node. So we will see how that happens, but essentially the mapper task will be created on this node and the task will read, perform the operations, and then it will once it finishes, it will inform that this read is complete. Okay, but the second read that it fires will not wait for the first read to complete. Okay, so this is how it basically because each of these reads may take a lot of time. Okay, so if one read waits for the other read to complete, then you will not be able to have parallelization, or you may not have so the entire throughput of the file system may come down. Okay, and finally, once all the read requests have been processed, uh, there is a close call on the HDFS client calls the close method, and the FS data stream data input stream object is then sort of deleted. Okay, so how does write happen? Okay, so now read is relatively easy. Now write starts with the create call. So the HDFS client uh, does the create call on using the distributed file system class, and then it talks to the name node and creates the file. Basically here what the name node does is it figures out a set of data nodes where the blocks can be written. Okay, and it sends the list of those data nodes to back to the HDFS client. Now with that list, the HDFS clients create this FS data output stream object. Okay, now when and then it calls a write packet. So once it has enough data to write onto the file system, it calls an actual write to the data node. Now here the data node writes, it creates a file in the local directory and it writes that file. Okay, but it also takes care of this pipelining. So what is pipelining? Pipelining is basically that every time block is written or a write request for a block is started, actually 3 blocks are written. Okay, so the client doesn't write all the 3 blocks. Okay, the so this writing of 3 blocks is called pipeline, and typically what happens is that the second block is written onto the same rack, but the third block is written onto a different rack. Okay, so the data node then creates another block on another data node, and it talks to the data node to write the data of this block onto that data node also, and similarly to a so this data node talks to the third data node outside the rack, and it writes the data there, and all of these data nodes they send. So this is called the pipeline write. Okay, and then they send back acknowledgements to the parent data node saying that the writing is successfully done, and this acknowledgement transports all the way back to the HDFS client, at which point it knows that the write has been successful. So this write is a very resource intensive operation. Okay, and this write is so this is called the pipeline writes, and again all the write requests are also started in parallel. So this is one write request to one data node. The client may also start another write request to another data node even before the acknowledgement for this write has come back. And once the acknowledgement for all the writes have come back, the 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 client may call the close method, and then the distributed file system may inform the name node that the write for this particular client is complete. Okay, so how does so this is something that I discussed in the last slide. So typically the replication factor of HDFS is set to 3. So the first replica is placed on the local node, on the node So typically it is the reducer which writes to the HDFS. Okay, and so the first replica, if there is space on the local node, that is how the reducer will be scheduled, because the reducer will call a write method at the time of scheduling. And so the first replica will be written on a local node, and then the pipeline write will start. So the second replica will be written on a remote rack. Okay, and the third replica will be written on the same remote rack. So the idea here is that there is only one inter-rack transmission for the replication. So clients read from the nearest replica, and this nearness is in terms of rack locality. And yeah, so this policy can be changed probably, but this is the random policy that is used, or this is the default policy rather that is used. Okay, now yeah, so name node, as it was mentioned, is the single point of failure. Okay, so what the name node does is it stores a transaction log, okay, in multiple directories. Okay, so it can store the transaction log in a directory on the local file system, or it can store uh, on another remote file system like a network file system or something like this. So I think we have already discussed this. So in conclusion, what we have seen is the structure of HDFS, the shell commands, the architecture of the HDFS file system, and the internal functioning of HDFS.